So today we're going to continue with our discussion on with interferometers. So we're trying to use interferometers as a tool to understand quantum physics. But interferometers are just one tool. An interferometer is something physical, right? Batsuno. So these are mirrors, beam splitters, photons, detectors. All of this is physical, something you can touch. It's tangible. And we're using this framework to look at different facets of quantum physics. Now, in our previous lecture, we kind of started off on the concept of quantum erasure. Now, this is a really interesting phenomenon, one of the most exciting bits of quantum physics. So since there's a 2-week lapse in our class, just like to do a quick recap from the previous time. Acha, let's get started. Come on. Silence, please. So our archetypal interferometer, a beam splitter, two mirrors, perfect mirrors, and two detectors. D1, D2, and our photon comes in the state ket 0, and this is the path degree of freedom, and we know what's going to happen. One of the detectors is going to click because there is interference between the two possibilities. There is a superposition state, and when the two subcomponents recombine, there is a constructive interference occurring here and destructive interference occurring here. And interference is also a phenomenon associated with waves. So this is where this photon is acting like a wave. All right, now instead of having 1 degree of freedom, we introduce a 2nd degree of freedom. We mentioned that this photon can also be polarized. Please stop this commotion. Now if this photon would be polarized, let's assume its polarization is diagonal. So the incoming photon, in addition to being on this path, also carries a definite polarization, and it is diagonally polarized. So the incoming photon is in a state ket 0 for the path and ket D for the polarization. And ket D is an equal superposition of horizontal and vertical. Now what's going to happen is that this beam splitter is going to do nothing to the polarization. It's kind of silent to the polarization, but it's going to create a superposition here. So the first beam splitter, P1, does nothing to the polarization, so that remains what it originally were, and you would get a superposition of paths. Now if you do nothing, you would just see that a photon is going to come out at this detector, is going to click and hit on this detector. This detector is going to fire with 100% probability, and if you were to measure the polarization of this photon, it's also going to be diagonal, because nothing is there inside the physical system that's going to manipulate the polarization. So this apparatus is kind of immune to any polarization effects. It does nothing to the polarization. However, let's change this scenario a little bit. So without any further ado, without changing things any further, this acts like a conventional Mach-Zehnder interferometer. Interference shows up, superposition exists, superposition exists, constructive interference takes place on this path, and this detector fires, lights up, the other detector remains silent. Good? So far so good. Now what I would like to do is I would like to place a polarizer here, and I would keep this optic axis horizontal, and I would keep this another polarizer here, and let's make this polarizer vertically polarized. And before the detectors, I also place polarizers outside the interferometer. So the interferometer ends up here, and then we have the detection system. But just before the detectors, I place a horizontal polarizer on this path, and I place a vertical polarizer on this path. So that's my scheme. Now what's going to happen is, let's look at the progression of the quantum state. First of all, if you forget about the quantum kinematics, how this state is going to change with time as it progresses through the interferometer, based on your understanding of the uncertainty principle and the concept of which path information, what is your guess? Which of these detectors is going to click? D1, D2, or both, or none? All of a sudden, both of these detectors are going to start clicking. Why is that? Yes, please.
When a certain detector clicks, you know which path the photon took, because the polarizer only allows the specific polarization to pass through, which means that it's already been polarized before.
Beautiful. So if this detector clicks, for example, so you don't need to do the quantum kinematics, how the state progresses. You can just use your knowledge of the uncertainty principle and mention that if this detector clicks, for example, it means that the photon hitting this detector must be horizontally polarized, because only such a photon would have propagated through this polarizer, otherwise it would have been blocked. So the photon coming out of the interferometer is horizontally polarized. If it were horizontally polarized, it must have come through this path. Let's call this path capital 1, and this path, let's call it capital 2. So this is capital 2 path, all of it. This is capital 1 path. So if this detector clicks, you would immediately tell which path the photon has taken. It must have taken this path number 1, which means you do have which path information. So if you look at this in an uncertainty diagram, this is path, 2 paths possible, 1 and 2. Here is momentum. So now you have information about the path and 2 possible momentums corresponding to D1 and D2. And if the other detector clicks, you will be able to infer from the click that the photon must have taken the second path. So by looking at the detector outcomes, you can tell which path the photon has taken. And when you have the which path information, which means you know the position, you will be uncertain about the momentum, which means you don't know which direction the outgoing photon is going to take, and it's going to hit detector D1 and D2 with the same probability. All right, so let's look at this from a quantum progression, state progression perspective. So now we've broken the kind of indistinguishability between these paths by placing polarizers. In other words, we have tagged the path onto the polarization of the photon. We are using the polarization of the photon to tag the path taken. We cannot directly measure the path because we cannot go inside the interferometer, but we transfer information of the path onto the polarization of a photon, and we can look at the polarization when the photon has emerged out of the interferometer. So we have tagged the path onto the polarization, and looking at the polarization we can tell what the path is. So we have information about the path. Which path information becomes available? So let's look at it from a perspective of dynamics. So after the polarizers, let's call this P1, P2. After the polarizers, we know that let's call this path ket 0, this path ket 1. Ket 0 corresponds to the horizontal going photon. So on the path ket 0, photon that comes out here must be horizontally polarized. So I can also, if you would like, I can also, before I do this step, I can also spell this out. This is 1 over under root 2 0 plus 1 for the path, and ket H plus ket V for the polarization. If you wish, I could also spell this out, expand this out, ket 0 tensor or dot product with H plus 0 cross V plus ket 1 cross ket H plus ket 1 cross ket V. Quantum physics is linear, all right? Linear means just like you have a sum of two numbers, and when you multiply the two numbers, you do multiplication one by one. It's very similar to that idea. By the way, this is now looking at 2 degrees of freedom of the same particle. So it's a bigger dimensional system. Now, if you look at this, at these 4 terms, it's a superposition state. Now involving 4 states. It's a superposition of 4 distinct states. Now what these polarizers are going to do, they're going to block certain terms. They're going to block, for example, this term and this term. This term is just going to be blocked by the polarizer. So with some probability, the photon is going to be blocked. So you're losing some photons in the process. But whenever a photon goes beyond, whenever a photon is detected, that photon has not been absorbed by the polarizers, and there's some finite probability that's going to happen. Because in this path, a photon that comes out must be vertically polarized. So there are 4 terms. 2 of these terms will be blocked. They will be subdued. They'll be annihilated. They will go away. Because the photon in this path cannot be vertically polarized. Therefore, this term cannot come out of the polarizer. Likewise, on this path, the photon that comes out here has to be vertically polarized. It cannot be horizontally polarized. So this term will also disappear. It will be blocked. And each of these terms has the same probability, 1 over 4. Square of half is 1/4. So 25% of the terms are like this, 25 like this, 25 like this, 25 like this. So if you just block out 2 terms, with 50% probability, a photon will progress beyond the 2 polarizers. Okay, so a new state will be created, because these polarizers absorb or let the photon go. So when a photon is absorbed, the coefficients will change. A new quantum state is going to be created. So when this happens, so if I would now pass this state through the 2 polarizers, I will create a new state, ket 0 crossed with H plus ket 1 crossed with V. All right. And I would like to normalize this state. So all of these terms have equal coefficients. So they are kind of symmetric. So what term should I write with each state? 1 over under root 2, because the modulus square of those terms must be 1. So there's a 1 over under root 2 with this new state that has been created. Now what the mirrors are going to do, ket 0 is going to ket 1, ket 1 is going to ket 0. It's going to flip the paths. It will do nothing to the polarizers. Okay, that's given to you in the problem. So with the mirrors now, mirrors M1 and M2, you'll get right. Now this quantum state you still cannot define which path the photon is taking. It's in a superposition. All right, this is a superposition state, isn't it? We have this sum here. This state, by the way, is an example of an entangled state. This state exhibits entanglement, and I'll explain what entanglement means later, but this is your first introduction to an entangled state, quantum entangled state. Now when the second beam splitter is encountered by this quantum state, let's see what's going to happen. 1 over under root 2, this ket 1 is going to ket 0 minus ket 1 over under root 2. Nothing happens to the polarization, plus ket 0 plus ket 1. These are what beam splitters do. Ket p. So I just kind of collect similar terms. I just factorize out ket 0 and I will get H plus V. I just put a 1 over 2 here, put a 1 over 2 here. All right. And then I have minus ket 1 crossed with so I can write this state in this fashion, can't I? It's just this kind of shuffling of terms. Ji.
How do we know when to bring in the normalization factor? Make up a normalization?
So we brought in a normalization factor here, a new normalization factor, because we know some of these terms disappeared. So a non-unitary process occurred, some absorption occurred, so a new state is created. So with each new state, we would like to put in a normalization constant. And since everything is on equal footing, if there are n terms, the normalization constant will be 1 over square root n. And that's the only point where we've introduced a normalization constant. Yes, please? ये वाला ये वाला तो यही मैं कह रहा हूँ कि at this point these terms are blocked, a new state is created which carries only these terms. So we have to decide on what normalization should occur. So here there are 4 terms. If you take the modulus square of half, it's 1 over 4. So 1 over 4 coefficient probability with this, 1 over 4 here, 1 over 4 here, 1 over 4, all these 1 over 4s add up to 1. Now with these 2 terms, you need to have 1 over under root 2. If 3 terms survived, you would have 1 over under root 3. So some terms are blocked, they go away. For example, let me give you an example for this. If I have a polarizer whose polarization optic axis is along horizontal and have an input state which is diagonally polarized, which is 1 over under root 2 ket H plus V. This is my input state. Will a photon come out of this polarizer? Will it come out or will it not come out? Not come out at all? It will come out with some probability, because what's going to happen is that this polarizer, so let's call this ket D, the probability that it comes out, any state that comes out here must be ket H. If a photon comes out, put a detector here, it clicks, it must be horizontally polarized. That's a property of this polarizer. So if it comes out, the output state is ket H. So how much ket H exists inside the input state? Just acting like a filter, it just lets some light come out. So that probability is going to be the overlap of the input state with an output state, if it exists, modulus squared. And this would be 1/2. So with 50% probability, a photon is going to issue out of this polarizer. If a photon comes out, if a photon were to come out, which happens 50% of the times, if a photon were to come out, what would be its quantum state? Ket h or ket h over under root 2? Ket h, right? It's going to be ket h. This term takes care of the probabilities, but the state has to be normalized. It's ket h. Got it? Now, this is the state that emerges from the interferometer, that comes out of the interferometer. And I can kind of write this in a sneaky fashion. I can write this as ket 0 crossed ket d, diagonal state, plus minus ket b, anti-diagonal state. But diagonal state is defined as this state, anti-diagonal state is defined as this state. Now, this is the state. Let's call this psi out. This is the state that comes out of here, okay? This is my psi out over here. By the way, if you input a photon into this interferometer, will it always come out? No, it's going to come out only half of the times because you blocked half of the terms over here. So it's going to come out half of the time. But whenever a photon comes out, which happens 50% of the times, it's going to be in this quantum state. And this is normalized. Now what we would like to see is we would like to measure the probability that detector D1 clicks and the probability that detector D2 clicks. Yes, please.
If the polarizer collapses the quantum state to either vertical or horizontal, how can it exist in a diagonal state after passing through them?
Sorry? Well, this is quantum physics. I mean, this is in front of us. This is how we explain this. Because it's really this state. It's not horizontal or vertical. It's horizontal and vertical. किसने पूछा सवाल? It's not horizontal. This is not horizontal or vertical. This is a superposition of horizontal and vertical.
But isn't the polarizer in the interferometer collapsing?
It has collapsed it here, but what it has created, if it were just this, I would believe you. If it were just this, it would believe, but now it's a superposition. And what the second beam splitter is doing, it's doing marvels. It's actually reconnecting the horizontal and vertical back together, as we've seen over here, and creating a new interference. This is interference. Quantum interference is creating this quantum state. Okay? So now let's see what's the problem. Yes, please.
Repeat this again, please, what you said right now.
So at the end we have a superposition of diagonal and anti-diagonal, and remember, it's not just diagonal and anti-diagonal. Each diagonal correlates with the path. Polarization and path are correlated, and this strong correlation is called entanglement. Really strong correlation. The path and the polarization are correlated, and that is what it means to say that the image of the path is on the polarization. The path is tagged with the polarization because it's easier to look at the polarization than the path. So we have transferred the information of the path onto the polarization. You measure the polarization, you can tell what the path is. But now superposition has been created, and the superposition is created because of interference. The second beam splitter is interfering the two paths and creating a superposition of diagonal and anti-diagonal states. So now we would like to find out the probability that D1 clicks. Now the probability that D1 clicks, let's look at this path. If this detector clicks, what should be the path of this photon? Ket 0. What should be the polarization of this photon? Ket h. So we look at the overlap of this state with so our psi out This is a big state. This is all of this. It's a 4-dimensional state. 4-dimensional because each one, this is a qubit and this is a qubit. Each one of them is 2-dimensional. It has a base, 2 basis states, ket 0, ket 1, 2 basis states, ket h and ket v. So when you combine the two, you get a 4-dimensional space, bigger space. And we represent that bigger, higher dimensional quantum state with psi out. So it's a composite of 2 qubits. So what we would like to do is we would like to find the overlap of this with what you've just mentioned. So we write the bra ket 0 tensored with ket h and take the modulus square of this. All right. Now let me show you how to do that. Things are really simple, and now you will realize the power of this bracket. This bracket notation, this calculus, which is called Dirac calculus, is powerful because it lets you physically visualize things. And this is the best way to learn quantum physics. All right, so I spell out this thing. It's 1 over under root 2, so I just bring it outside. Bra 0 product with ket h and my kind of all right. So now how do you find out this inner product? So you look at the first. This system is a composite of 2 systems, path and polarization. When you write a cross product, a tensor product, a direct product, sorry, or a tensor product, the thing that comes before this sign is the path degree of freedom, and here you have polarization. So path combines with path, polarization combines with polarization. Each subsystem talks to its own subsystem. So each bra talks to its corresponding ket. All right? And you don't mix the two, you don't hop between the 2 subsystems. Path talks to path, polarization talks to polarization. So what you would do is 1 over under root 2. This bracket 0 is path. It talks just to this. It doesn't care about this thing, right? So you would do the inner product of ket 0 with ket 0. Now this is just a number. It's a scalar. It's a dot product. It's a scalar. It's not a ket or a bra. It's a scalar. It's just complex number. And then therefore, this polarization talks to this polarization. So you form the inner product of H with D. So you multiply this out with H and D. Okay? That's how you form this inner product between these terms. All right? And the other inner product between these terms must also be constructed because of the linearity of quantum physics. So this will give us minus, can you spell this out? Bra 0, ket 1, bra H, ket A. Right? And now all of this modulus square, right? All right. So this comes out to be 1/2. Now what about this term? So this is a scalar. This is 0 anyway because of this orthogonality condition, right? This is 0. No matter what this is. All right. So this is 1. And what is this? 1 over under root 2. This term is 1 over under root 2. Why? Because we have defined it to be in this fashion. This is how we've defined ket D. Ket D is this plus ket V over under root 2. So the overlap of this state with ket H must be 1 over under root 2. So this is 1 over under root 2, and you take the modulus square of this, it's going to be under 2. So your answer is 1 by 4. All right. Now what does this mean? So this means that the probability that detector D1 clicks is 1 by 4. Can you find the probability that detector D2 clicks?
So can you repeat the last segment?
So this is 1 over under 2. This is also 1 over under 2 from this thing. So 1 over under 2 multiplied by 1 over under 2 is 1/2. Take the square, get 1 by 4. So what is probability that D2 clicks? It's going to be 1 by 4 again. So why don't these probabilities add up to 1/2? 1. Because of blockage of the which polarizers? No, the ones at the end. We've already taken into account the impact of these polarizers. A photon is going to come out half of the times. A photon comes out half of the times. But whenever a photon comes out, half of those times some detector will click. And each detector will click half of those half times. So each detector is going to click with the probability 25%. 50% of times no detector is going to click. And that's so 50% of the times a photon is going out, 50% of that 50% is not going to show up. No. So this is within the new state that has been created. So if you overall if you just correlate with the number of photons coming in, it's going to be 1 by 8. Yes, please.
Are these probabilities given that the photon emerges from the interferometer,
Yes.
or the overall probabilities?
These are just when the photon emerges from the interferometer. So overall, if you compare with how many photons are going in, it's 1 by 8. Yes, please.
Do we write 1 by 8 or do we write 1 by 4?
You just write this and explain what's going on.
We explain half the time the photon comes out and half the
Right. So this is with respect to this. Whenever a photon comes out, the quantum state here is going to be this state. In this case, 25% of the times D1 clicks, 25% of the time D2 clicks. Do we have interference? No, no interference. Because a photon is coming out at both paths. ये बात बहुत ध्यान से सुनने वाली है. No interference. A photon comes out of both paths. Both detectors click. Very dissimilar to our original configuration when we had no polarizers whatsoever. And we have lost interference, which means we have now information about the path. We have which path information available to us. Because now telling which detector clicks, we can tell which path the photon has taken. So when we can tell the path, we know the position, we can't tell the momentum. So each of these detectors can click, which means that the momentum of the photon that is emerging from the interferometer gets totally uncertain. All right. So this is kind of neat. We have broken our interferometer. It's no longer an interferometer. The wave kind of notion just withers away. Now the photon is acting like a particle because now we know which path this photon is taking. And each of these detectors is equally likely to click. Interference withers away, it goes away. No interference, which path information available? So we have no interference, which path information available. And we can tell from the outcome which path the photon has taken. All right, so far so good, but let's take a twist. Let's twist this a little bit and let's sprinkle in some spell of magic into this. Now what we're going to do is have this interferometer in the same kind of configuration. D1 polarizer 1 P1 polarizer 2, a photon coming in into the state ket 0 crossed with ket D. Okay, this is our incoming photon. By the way, question, how can we create ket D? How can we create a photon in the state ket D? Right, just have, so this can be created by having a photon in any state whatsoever and passing it through a polarizer whose optic axis is diagonal. So any photon that comes out must be diagonally polarized. By the way, the input state cannot be anti-diagonal because otherwise you will never get a photon out. Anyway, this is how you create a photon in a particular polarization. Yes, please. Sorry. Now the magic that we would like to do, we know that this configuration collapses the interference and it provides us with the which path information because now we have knowledge of the polarization of the photon that is coming out.
So are we having 3 mirrors or 2 beams?
Now what we would like to do, let's take these. Remember this thing here that I put in a box forms a measurement in quantum physics. A polarizer followed by a detector is a kind of a measurement that I'm doing because this measurement corresponds to the act of finding the inner product of the input state with some states associated with the measurement outcome. This is the standard process in quantum physics. So this bra is telling us the orientation of the polarizer just before the detector, isn't it? And this is telling us the path at which the detector is placed. Now what we would like to do is, after the photon has gone out of the interferometer, we just look at these polarizers, and instead of this orientation of the polarizers, let's still have 2 polarizers, but let's have both of them with their optic axis along the diagonal. Both of them with their optic axis along the diagonal. If I look at the state at this position just before the detectors, psi out, isn't it going to be the same as this state? Is it going to be the same as this state? Yes, because we have changed nothing inside the interferometer. We've done nothing, all right? So the output state just before the detection polarizers is unchanged from our previous discussion. It's going to be 1 over under root 2 ket 0 cross D minus ket 1 cross antidiagonal. Now, in your good imagination and in good faith and with some good manners, can you please identify what the probability would be for detector D1 clicking? Half, 1/2. And what's the probability that detector D2 clicks? 0. Because along the path, this path, the measurement bra is really ket 1 cross ket D. And if I were to take the overlap of this state with 1 over under root 2 ket 0 crossed with D minus 1 crossed with A, this will be wholly and solely 0, because this path is orthogonal to this path, whereas this ket is orthogonal to this ket. So no photon emerges here. No photon comes out here whatsoever. Only a photon comes out on detector D1. That's it. Even though the probability is half, because it's going to be blocked half of the times over here. So you put in a photon, of the half photons that come out, half of them will show up here and the other half will just be annihilated. They will be absorbed by this analyzer. But only one detector clicks. Isn't this back to this interferometer that we started off? Only one detector clicking. Now by telling this detector clicks, can we tell which path the photon has taken? No. We have lost which path information, even though we had tagged the paths with polarizers, but we have erased which path information. Information has been erased. So this kind of a setup is called a quantum erasure. Quantum eraser. And this phenomenon is called quantum erasure. Now the good thing is, does light travel with the finite speed? So in a quantum erasure, which path information is washed away? We've erased which path information. That information should have been available to us once the photon has come out of this interferometer. Its polarization tags its path. But now, by looking at something in the future or in the present, we are kind of erasing information that would be otherwise available to us, information that the past would have given us. Now, in order to kind of highlight this phenomenon a bit further, suppose this is my interferometer. Very small one, and I have two polarizers. Small polarizers, right? Now what I would like to do, to place a polarizer here very far away. And a detector, and I'm not drawing the orientation of this polarizer for the time being. And I have a kind of all right. So this is my interferometer. A single photon comes in. A single photon comes in. Now this photon travels with a finite speed. It's in air or vacuum, speed of light. Suppose this is 1 millimeters. This interferometer size is 1 millimeters. So it might take, say, a nanosecond for the photon. You know when the photon is triggered because you have a laser light here. You know when a photon has come out. You can time it. Now it just takes 1 nanosecond for that photon to traverse this interferometer. But then you do this kind of long distance kind of detectors very far off, say light takes another millisecond, 1,000 times longer to reach these detectors. Now these kind of polarizers are your choice. What orientation would you like? Okay, you can make a choice later in time, after the photon has emerged from this interferometer, right? So you make a choice later in time. So now such an experiment is called a delayed choice experiment. A delayed choice quantum eraser. Now if you were to choose, let's call this polarizer P3 and let's call the polarizer at the top P4. If P3 and P4 were both horizontal and vertical, no interference would take place. Which path information is available to us? And which path information can only come from inside the interferometer, because path is only inside the interferometer. So if you choose your polarizers in this configuration at leisure, after the photon has come out from the interferometer, because you wait long enough, then if this were the configuration of the polarizers, no interference. Which path information available? So far so good, because you can tell which path the photon has taken by looking at which detector clicks. However, if you adjust these polarizers in the diagonal configuration, even though the photon has left the interferometer long ago, so you do not have any control over the path and the superposition and whether it's a wave or a particle. It has left your apparatus long time ago. You will see interference back again. So interference reappears and which path information is erased. So by doing a delayed choice experiment, you can alter the outcome of an experiment that has occurred in the past. So popular science writers generally write this as the present can alter the past, or the future can alter the present. So facts were already available to us, which path the photon has taken, but those facts can be erased. Information can be erased. And by the way, there is a very neat experiment that actually explores this. I'm going to explain that experiment in a minute, but any questions about this? I'm going to show you some experimental results that describe this. Yes, please. जब हम डायगोनल कर देंगे सिर्फ एक क्लिक है, और ये हमारी चॉइस है कि हम इसको डायगोनल रखें, हम ये वाली कॉन्फ़िगरेशन रखते हैं पोलराइजर्स की, या ये वाली रखते हैं. It's our choice. We can make a choice later in time. We can erase facts as they were available to us later in time. As the photon has now come out from this interferometer long time ago. All right. So yes, please. बिल्कुल रख सकते हो, मैं आपको दिखाता हूँ रिजल्ट्स.
If we had diagonal and anti-diagonal, would we get both?
Get both. Yes, please. No commotion so far. I'll give you a break, but I'm going to show you something. Yes, please. Why? So interference, why is this special? Interference can only take place inside the interferometer. Isn't it so? Because only here is the possibility for interference to take place. Now you are determining whether interference takes place or not taking place. Suppose a detector clicks on one detector. Somehow it has a pause for a minute, it has a consciousness. It says that I would only like to take this path and make a click on this detector. This path must destructively interfere. Now once a photon has left this interferometer, How can it change its mind in the middle? By depending on the mind of the experimenter, the observer, who's far away. The observer can make any choice whatsoever. Now the photon has already interfered or not interfered because it has left the interferometer. Now the choice of the experimenter, because this is totally in our this is a new consciousness, this is the human consciousness who is controlling the polarization of these polarizers. A new consciousness is determining what has happened to an object it's observing. So there's really no reality about the photon. The photon does not have a fixed path. It's very hard to say that the path of a photon is a property. It all depends upon how we look at it, how we measure it. So the objectivity is kind of sacrificed here. It's upon the subjective choice on how an experiment is done. So, by the way, let me first show you some examples for this. As I mentioned, can I just want to. Yes, please. Questions? Yes, please.
Can we say that these experiments were successful in attempts to disprove Heisenberg's certainty?
No, the uncertainty principle is still at work.
No, that's what I'm saying. That
They were not designed with that kind of intent in mind. Yes, please. Yeah, these questions are really important. They're important for everyone. Yes, please. Sorry, huh?
We change the polarization once and then we change it again. उससे कोई effect पड़ेगा? Why will it happen?
So it depends upon if the photon leaves the final polarizer just before the detector. It depends on that configuration. If it has left that polarizer, that will determine what the outcome of the experiment is. No, then it will not impact it. It depends upon what happens when the polarizer sees the photon. Okay. So this is an experiment that we do in the lab. So here is a source of photons. This is our interferometer, the beam splitter, two beam splitters. So what this initial polarizer P naught does, it creates the diagonal state. You need a polarizer to create a diagonal state. Now what we have a screen over here on one of the paths. As I mentioned in the previous lecture, if this beam is large in size, you can see the pattern interference or no interference in one go on a screen, on a big screen or on a camera. The camera tells you straight away whether interference occurs or it doesn't occur. Now I have two polarizers in the two paths similar to the polarizers that I've drawn here. Same thing, one is path 1, the other is path 2. If the polarizers are, both of them are parallel, I'm using a different kind of configuration. If both the polarizers are parallel, I cannot distinguish between the paths, right? Because if a photon emerges from this interferometer, I cannot tell which path the photon has taken. So that's another way of saying that the polarizers don't exist. It's as good as the polarizers don't exist, even though the flux of photons will be reduced because the polarizer is going to block something. Anyway, if the two polarizers are parallel, do I have which path information? No. Does interference occur? Yes. So this is the scenario that I get. I get interference fringes from photons. By the way, this experiment is done with not with quantum light but with classical light, and I've chosen this outcome because it's visually more revealing. I can show you data from real photons, quantum photons as well, but let's put that to another time. If the two polarizers are crossed, which means one is horizontal, the other is vertical, as we have over here, then I am tagging the path onto the polarization. So if I look at which detector clicks, I can really know, by looking at the detector, I can measure its polarization and tell which path it has taken. So in that case, the interference fringes disappear and I get a kind of blob, no fringes. Which path information is now available to me. If I were to measure the polarization of this light, I can place a polarizer here. If I were to measure its polarization, I can tell which path it has taken. I've just chosen not to measure the polarization, but if I were to do it, I would get which path information. Now the other scheme is if I were to keep the one polarizer fixed and rotate the other. When the two polarizers are parallel, I will get strong fringes. Scenario A is when both the polarizers are parallel. When they are parallel, I do not have which path information and strongly visible fringes come about. If I start rotating one of the polarizers, gradually the visibility of these fringes diminishes. So I get partial information about the path. This was a question in one of the earlier classes as well. So the visibility of fringes goes down, and eventually at this scenario J, P2 and P1 are crossed with one another. So this is it's not our erasure experiment so far, it's just this experiment in a different sense. Now what we could do in order to look at erasure, what we need to do is place a polarizer over here and keep these two polarizers in crossed position. When they're crossed, I have which path information, but I can erase that information by placing a component after the interferometer, after the photon has been able to make a choice of whether it's going to interfere with itself or not. So by my choice, I'm not a part of the experiment. My choice to place a polarizer after this beam splitter or not. So my choice determines whether that photon is a wave or a particle. My choice determines whether that photon is going to interfere or it's not going to interfere with itself. And long after it has come out of the region of space where interference is even possible. That is the kind of beauty and the excitement about this. So in the last experiment, what we could do is we would actually place another polarizer, P3, at the output. P1 and P2 are now crossed. When P3 is in the diagonal form, I get these fringes, and when P3 is horizontal or vertical, the fringes disappear. In this case, which path information, which was previously available with me when the two polarizers were crossed, has now been erased, and I recover information fringes. Now this polarizer can be very far off, very far away, but since light travels at really fast speed, if I were to do it in real time, I would have to take the detector probably out of Lahore. But there are other experiments on a cosmic scale that allow us to do that, and after a 10-minute break, I'm going to kind of give you an example of such an experiment. Let's have a 10-minute break. Let's change the taste a little bit. Let's talk about electrons for a moment. And now I'm not talking about the spin of an electron, but the path of an electron. So suppose I have, how can I produce electrons? A beam of electrons? By heating a kind of filament. So electrons come out. Now this electron comes out of a slit. So I produce beam of electrons, it hits a screen with a slit. So these electrons then come out of the system, they diffract, they kind of broaden, as it happens with in most of physical scenarios, and then you have a screen with two slits, S1 and S2. And here I place a screen or a camera or a screen that detects electrons. So whenever an electron falls on the screen, it produces a blob. So this could be a photographic film. You develop it later, you can see kind of some regions get dark. They show that electrons have fallen onto those regions. Now when you have this stream of electrons coming in, what kind of pattern would you see on the screen? You see interference fringes, which means that electrons behave like waves. Okay, so you see fringes, bright, dark, regions and in your A-level physics you've already know, I don't want to go belabor this point, you know that these electrons are behaving like waves and there's a wavelength associated with it and their wavelength is associated with the momentum. We already know that, the de Broglie relationship, which is also sometimes written as H bar K. So this is the de Broglie relationship. You can look up any modern physics book and this will kind of give you pages and pages on what this really means. But these electrons are behaving like waves. And this actually experiment was done by Davison and Germer in the 1920s, I think. And they showed that electrons are waves. Thomson in 1896 proved that electrons are particles. But then Thomson's own son, Thomson Jr., proved that they are waves, followed by Davison and Germer's experiments. You can look up any modern physics book and you'll find interesting accounts of this. So electrons are behaving like waves. And these are interference fringes. And if you would like to make a plot of intensities versus distance along the screen, this is how fringes look like. Remember the cosine square things which we show with photons, exactly the same mathematical form. All right. There was a kind of competition in the early 2000, I think, which asked all the readers in the world of a magazine to come up with their choice of the most influential experiment in all of physics. And by a big margin, this experiment, called the double slit experiment, won. Because all of quantum physics is embedded in this. All of quantum physics is embedded in the interferometry experiments that we've talked about. So we learned all of quantum physics really. Now it's just a matter of kind of brushing up your mathematics and doing practice and so on. So you get interference fringes. Now the good thing is that if this source of electrons in the beam was so dilute, so sparse, that only one electron comes out at a time. So in this apparatus, there is only one electron inside this interferometer. This is also an interferometer. So there is only one electron inside the interferometer at a time. And then you fire one electron, bzz, it can go through the system, wait for some time, then fire the second electron, and then over time, over hours and minutes, probably a day or so, you build up this kind of, see what areas have those single electrons landed at, and you develop this film, you will still get interference fringes. So an electron is also interfering with itself, even though it's a single electron in the system. But in order to tell that the electron has interfered, you need to repeat the experiment multiple number of times. So if you want to detect in the photon experiments where interference takes place, one detector click cannot tell you. You just have to repeat the experiment a number of times. And you see there will so these are the kind of dark detectors. Dark, no photon falls here, no electron falls here. So this detector never clicks, but these detectors always clicks. So you see the correspondence between this notion and the notion that we've been discussing with photons. Now here, sometimes you say that the electron is behaving like a wave. It's interfering, it's behaving like a wave, and it happens with a single electron. And why does it happen? Because if I associated with this path a quantum state ket A, associated with this path a quantum state ket B, just as I've done with electrons ket 0 and ket 1, I can call this ket 0, ket 1. Here, that single electron is in a superposition ket A plus ket B over under root 2. All right? And this is leading to the interference. So superposition of that single electron also exists inside this region. Some regions you see constructive interference, others you see destructive interference. So this is the kind of broad idea. The electron is behaving like a wave, you see interference, superposition exists, and even though you can't split an electron, it's a lepton, it's a fundamental particle. You can split protons and neutrons, but you can't split electrons. These are fundamental particles. Therefore, you can't say that the electron, half of it is going through S1, half of it is going through S2. Just like you can't say that the photon cannot be split, the electron cannot be split. So it's just one electron interfering with itself, this giant wave, this giant quantum state that exists in a delocalized fashion inside this region. All right, so far so good. Now, can you tell which path the electron has taken? No, you can't. Just like you can't tell which path the photon has taken. So suppose you're over clever, and in fact this was the raging debate between Bohr and Einstein. So suppose, so this was Bohr and Einstein's debate. So they thought, they communicated amongst one another. They thought, suppose I put roller wheels on the screen. Roller wheels. So these roller wheels can turn in any direction. So this screen can go up or down. So if an electron kind of comes onto this path and goes up, it transfers some of its momentum to the screen, and this screen moves down. It gets a kick and it moves down. The screen can go up and down. If it goes down, electron takes the upward path. If the screen goes down, goes down, the electron has, if the screen goes down, the electron has gone up because of conservation of momentum. If the screen goes up, the electron has gone down. So, which really means that by looking at the motion of the screen, you can tell which path the photon has taken. A simpler way to think of it is not these roller skates, but suppose you have a light source here, a small kind of single photon source, a small weak light source, and when an electron passes close to this light source, it lights up. So if it lights up here, if there's a spark here, you can tell the electron has taken the upper path, and there's a spark here, you can really say that the electron has taken the bottom path. So but if you were to tell the path, and if you eavesdropper is just spying on the path of the electron, this light source, then you would actually break the interference pattern and you see a big blob. The interference goes away. So now you have which path information, but you're uncertain about the momentum. You do not see interference fringes. Interference fringes can only appear if there is some kind of definiteness about the momentum, because momentum is related to k is related to the wavelength, fixed wavelength, wave nature. Only if there's a definiteness on the momentum, you will see interference fringes. But that's mutually exclusive with the which path information. So this is also the uncertainty principle for electrons. Same thing, same idea, same big idea, different physical manifestation. Now, so this is the wave-like experiment one could do. So there are bright regions and dark regions if you were to see interference fringes, but then you have no information whatsoever on the path that single electron has taken. Got it?
सर हमारे पास जब which path information obtain होती है तो momentum uncertain हो जाता है because या तो roller skate से absorb हो जाता है screen में या light से spark up होता है.
देखो या lights use करो या sparks use करो, एक use करो.
मतलब दोनों sources में से किसी एक में तो वो difference क्या आता है? Momentum change हो जाता है at that point.
Forget about the roller scale. Let's focus on the light source. If there's a light source, photons have momentum. So probably the section of the modern physics class is going to deal with this. So the photon has a momentum E over c. All right. So this momentum, this is the energy of a photon, hf over c. A photon has momentum. When this photon coming out from this light source hits the electron, it transfers some of its momentum to the electron. So the momentum of the electron gets fizzled out. I mean, it changes, smears out. And this was the traditional way of describing the uncertainty principle, by the way. I have described the uncertainty principle in terms of information. Okay? But most textbooks describe it in the way that you've mentioned, which is the kind of classical traditional way. But you can explain it in that way too. So the photon has momentum, that momentum is transferred to the electron, and its own momentum becomes kind of crazy. And
So in quantum wave, we just describe it with the with path information.
you can describe it in that fashion too, if you are kind of hooked up to the mechanical view of the universe.
Yeah, I was asking that
Both of these approaches are correct.
there is no other prospect in the quantum way rather than the which path information.
No, that is also quantum. That's also quantum. That's also quantum, but that's a traditional approach of describing it. Now, suppose I were to do this experiment in this fashion. So I have my electron source, electrons coming in, one screen just to kind of produce a collimated beam of electrons, and instead of this screen with two slits that are causing the interference, I have one kind of detector here, D1, and this is an electron detector. It detects electrons. And another electron detector D2 here. So I do not have a screen and I do not have double slits, just two detectors. One is those electrons are coming, one is pointing towards the electron from this direction, the other is pointing it from this direction. Now will I see interference here? Just think in terms of information, momentum, path, uncertainty, no interference, which means that it's equally likely that either of the detectors is going to click. But if this detector clicks, can I tell the path the electron takes, cat A or cat B? Yes. I have collapsed that superposition and I can tell that the electron were in the state cat A, it has taken the upper path. So if this detector clicks, I know that the electron were in the state cat A, and I know it must have taken the path that goes up. So I have information about the path. And here if this detector were to click, I still have information about the path. And if I were to repeat this experiment multiple number of times, the probabilities that these detectors are going to click will be equal. There will be equal symmetric dispersion. Not half-half, because sometimes electrons can go here, sometimes electrons can go here, but they will be symmetric, half-half, like examples that we've seen. So this is interference, no information about the path, and if I try to be over clever and try to find out which path the electron has taken, the interference diffuses, it just goes away, washed out. Here, I have information about the path, but I do not see bright and dark regions, right? So there's an equal propensity for the electron to fall on either of these detectors. So we described the photon experiments. These electron experiments work in an entirely analogous fashion. Yes, please.
Sir, you mentioned before when we are getting the which path information, we won't be getting fringes. Then why are we getting fringes when we have a light source there?
No, when we have light source, the fringes will disappear. Now let's connect this with the delayed choice thing. Is anyone fond of cosmology? All right. My friend at the back, do you know what gravitational lensing is? You're not that strong? You're not that fond? Okay. Yes, please.
Well, if you have like a really massive object and there's some source of light behind it, when the light shines through around that object, it will bend because of the gravitation of the object.
Right. So suppose I have a big, massive cluster of mass, really big distribution of mass in the outer expanse of the atmosphere of space, like a galaxy, a big galaxy, and you have some source of light behind it, and this is your observation point. This is suppose the Earth. How old is the Earth? Sorry? No, 13 million? It's about 4.5 billion years old. How old is the universe? 13.8 billion. So there was a universe before the Earth existed, and light takes its very high speed. But suppose there was a light source that emitted electrons. Let's first talk about gravitational lensing. What gravitational lensing means is that if light comes from this light source could be a kind of supernova explosion, or it could be a quasar which is strong light sources. Light could be X-rays or gamma rays or visible light. That's besides the point. But as it passes through this massive object in space, light gets bent. So this is similar to if I have a lens and light comes from a source. Since the source is far away, all these rays are parallel to one another. So light gets bent, right, and it gets focused. But mass can also bend light. This is Einstein's theory of general relativity. Mass bends light. Because space-time gets curved near massive objects, light travels in straight lines in space-time, but since space-time is curved, it appears as if the light is bent. So light can bend in this fashion or in this fashion. And that's why the apparent position of this object might be different. So this is the real position of the object and this is the apparent position of the object. So the apparent position of this light source can change because of the bending of light. So this is a phenomenon that astronomers observe. Sometimes you see a ring outside. If this is a homogeneous distribution, you see a ring of light around this object. It's called an Einstein ring. So this is the phenomenon of gravitational lensing. Gravitational lensing. All right. Now suppose light from such a source is very dim because this supernova or quasar is really far off. So suppose this supernova happened say 12 billion years ago. So this light has traveled 12 billion light years to reach the earth. Well before our earth was made. Well before human beings came into existence, which is about 500,000 years ago. Well before any one of us were born. So that light that has emerged from this quasar has been originated from really far off. And those photons that are reaching the earth, they are far and few. Because it's a really dim source, because of the vast distance. So you might get a photon every hour. Just one photon every hour or a photon every day. It's such a weak light source. You really have single photons coming in. Now, if you do an experiment on Earth and look at this light source, this supernova, will that photon interfere with itself? So now you have two paths possible. Let's call this path ket A and this path ket B. This is like a giant interferometer of the cosmic scale, isn't it? Now, is that photon interfering with itself? Now, it has been issued, it has been traveling in the vast expanses of the cosmos for billions of years. It must have made up its mind whether it interferes or not, or it would have interfered or would have not interfered. It should be obvious to you. But now your choice of the experiment is determining whether it has interfered or not. So here you could do two kinds of experiments. You could put a screen with two slits, and if you would put a screen with two slits and just single photons coming in, you would see an interference pattern. And if you had two telescopes, so if the arrangement were like this, this is our Earth, and you had two telescopes, one telescope pointing up, the other telescope pointing in the slightly different orientation, then you would never see interference. So depending on what you do well into the future, billions of years into the future, you can determine whether a photon has really interfered in the past or not, because any interference that is bound to happen has happened really far back in time. So this is an example of delayed choice. By the way, in this experiment, here. If you had an arrangement in which this electrons travel at slower speeds than photons, don't they? Can you find out the speed of an electron? So how do you accelerate an electron? With electric field. So I'm an experimentalist, so I always like to talk about how you do things. So this electron, if you pass this through a potential difference V, it accelerates. Its new energy becomes VE, and this equals half mv square. So you can find out the speed the electron takes. The electrons can have different speeds. So how do you select electrons of one speed? एक और क्या डाल दें? So the best way to do this, you have two slits, and have two rings, and there's a slit in each ring, and the slit is small, and you move one ring with a certain speed, the other ring with another speed, and you times the angular speed such that only electrons at a certain speed can pass through, and you keep the distance between these rings fixed. This is how you select velocities. Anyway, suppose electrons travel at slow speeds. You have the choice that this detector, and behind these detectors, behind the screen, these are two detectors here. So you have a screen and two detectors. If the electron falls on the screen is opaque, the electrons do not pass through. So now if you had the choice of kind of having this screen in position or moving it out of position. So you have the screen in position, you will see fringes forming on the screen. But if you move the screen out, the fringes will go away and you will see the detectors clicking, and you will not see any fringes. By the way, you can have multiple detectors as well. Can you? So this is another kind of, I'm not going to into this debate. So you can choose what kind of measurement you are able to make. This is delayed choice quantum erasure. Now I can take 2 or 3 questions before I move on. Yes, please.
Is it the same principle that is used in James Webb telescope?
Sorry?
Is it the same principle that is used in James Webb telescope?
So James Webb telescope has these hypersensitive. Please. How are you? Assalamu alaikum.
Thank you. I'm interrupting you.
No. I just want to introduce you to the class, please. So I want you to introduce to you in the last 5 minutes of this class Professor Yusuf Sabuti. He's a well-known figure worldwide in astrophysics, but beyond that, there are many more aspects to his personality. He did a PhD from the University of Chicago. He was a student of an astrophysicist who won the Nobel Prize. He was born in Lahore. Can you name this astrophysicist? Not Abdul Salam. Abdul Salam wasn't born in Lahore. It's Chandrasekhar.
Abdul Salam was an astrophysicist.
As well. So he was a student of Chandrasekhar, but he's worked very closely with Abdul Salam. And beyond that, in Iran, Professor Sabuti has founded this international institution called the Institute of Advanced Studies in Basic Sciences in Zinjan, and is considered to be the doyen of physics and mathematics and astrophysics in Iran and the developing world. So I just requested him to come to my class. He's going to give a lecture tomorrow. I just requested him to come to class and inspire you with a few golden words. Please.
Thank you very much.
I've always been fortunate throughout my life to be associated with young faces like yourself. I'm a veteran lecturer. I have began my career in lecturing from goes to schools, high schools, colleges, and university. Can you guess for how many years? Almost 70 years. Almost 70 years. Thank you. And at certain stages in my life, Professor Tassi said, I've been fortunate to be associated with Chandrasekhar, one of my peers, and also Professor Abdul Salam. During 1960s, I was a student at the University of Chicago, where every day I would pass Chandra's office to go to my office in the basement to continue. And I very much learned from not only physics, I learned physics and astrophysics I learned from him. I learned many other things. The way to look at at physics, at the life, for me, they were quite inspiring. And later on, my association with Abdul Salam in ICTP, in the ICTP had one Council of Scientific what I forgot. Anyway, it was a UNESCO and International Atomic Energy Agency appointed a body to overlook the activities of the ICTP. And for a few years I was also a member of that committee, along with a dozen of physicists from around the world. We would sit down and see how ICTP was doing its work. And also in the TOAS, the World Academy of Sciences, again created by Abdul Salam. Abdul Salam's idea was what I learned from Abdul Salam. The developing countries cannot compete with the developed countries unless they master the source of their power. The source of the power is not economy, is not their arsenals. It is the basic sciences. Unless you understand it, unless in developing countries you can say that, okay, you Europeans, you Englishmen, you Frenchmen, you Americans, if I am also comparable to you in understanding what physics is, what mathematics is, what biology is, then you can stand up and say that I am equal to you. That was what I learned from Abdul Salam. Is that enough? Thank you.
So thank you very much.
Yeah.
Inshallah we'll meet on Tuesday. बहुत शुक्रिया.